So we're going to start on lesson 26. This is not letting me zoom in. There we go. Okay. Which we're going to start talking about. This is chapter 16, so this is the first lesson for exam 4, which is going to be over 3 chapters, kind of our longest unit of all of them, but it's going to be over thermodynamics, electrochemistry, and nuclear chemistry, with the hardest of those probably being the electrochemistry chapter. I cannot spell right. These other 2 chapters tend not to be as difficult for students. Okay, so we're going to start talking about a field of chemistry called thermodynamics, and we're going to start with talking about the 3 laws of thermodynamics. So the first law, and you need to make sure you know these laws pretty well, it says to define it, and so we can define it using a formula, which I like formulas for the most part, as long as I know the variables. So the variables here are the change in internal energy. And you guys may remember we talked about thermodynamics last semester just so briefly when we did heat and work, specific heat capacity. So this isn't brand new material to us, but we are going to add some things to what we already know. So the change in internal energy is going to be equal to the heat and the work, the sum of those 2 of our system. And so another way of defining it can be with words. And this is going to be that the energy can be converted from one form to another, but it cannot be destroyed. And so you might be thinking to yourself, this sounds like a conservation law. And it kind of is. It's saying that we cannot create heat, energy, work energy, but we can convert it. We cannot destroy it. It's going to be 100% converted from one form to another. And so that's our first law of thermodynamics. So when we're talking about, the title of this is called spontaneity, okay, which is to be spontaneous. So there are some main parts of the study of reactions in general chemistry, and we've talked about some of them, which is enthalpy. Do reactions use or produce heat? So is it endo or is it exo? Then we talked about kinetics. How fast does a reaction occur? This was our rate. Then we did equilibrium for a long time, capital K. How far will a reaction proceed? Will it proceed all the way to produce products? Does it produce very little products? How does it relate to Q? So this is what we've spent a lot of time on this semester. Now, spontaneity is going to be, is the reaction favorable? Okay, that's what spontaneous means here. Is it favorable? If it's not favorable, we're going to call it not spontaneous. Wood does not spontaneously ignite. That is not a spontaneous process. Here is a YouTube video, but we're going to talk about some examples of some spontaneous reactions. Okay, and so an example of a spontaneous reaction would be mixing baking soda, which is a base, and vinegar. Okay, when we mix those 2, we see bubbling, fizzing. Depending on the amount, the amount of reagents, there might be heat. There we go, eyelash on my iPad. Okay, now what I want you to do is keep an eye out for discussion board opportunity to list ideas of other reactions. Okay. So the thing about these processes, when we say that they're spontaneous, that's great, but they're only going to be spontaneous in one direction, not in the reverse. So when I mix baking soda and vinegar, and that is spontaneous, it's not in opposite. It's not true in the opposite direction. I can't mix the products that were formed as reactants and then produce baking soda and vinegar back. So the reverse process would be considered to be non-spontaneous. Okay. So let's practice identifying spontaneous in which direction. So identify the following as spontaneous, spontaneous in the reverse, or in equilibrium. So water at 40 degrees Celsius gets hot when a piece of metal that's at 150 degrees Celsius is added. So if we think about what this looks like, we have a beaker of water. Let's get a nice watercolor. It's at 40 degrees Celsius, and I'm going to input a piece of red hot metal. And the heat is then going to leave Q and warm up the water. Okay, those are arrows and Q's. So we would say that this is spontaneous. It doesn't take any work for that water to heat up. Okay, it's spontaneous in the forward. Right? Once you put the metal in there, you don't have to do anything else. The metal will eventually cool off and the water will eventually warm up. And we defined this in this way when we did calorimetry in chapter 5 last semester. The second one says an empty bottle is opened in a room that has had an air freshener sprayed in it. All of those fragrance molecules collect in the bottle. All. So what that means is if you were in a room and you opened a bottle, there was an open container and somebody came through and put air freshener, all of those freshener molecules, instead of dissipating about the room like this, evenly distributed, according to kinetic molecular theory. And I can't draw a real bottle, so I'm just going to try and draw an Erlenmeyer. Instead, all of those air freshener molecules would collect inside. And if you remember back to kinetic molecular theory, we said that gas molecules are going to want to evenly distribute around a room. They're not going to have any sort of incentive to collect in a corner and say, we're going to stay in this corner and this is oxygen's corner. So this is against kinetic molecular theory. Tells us that this is not spontaneous. It would take energy to corral all of those air freshener molecules and shove them into your bottle. Now, some of those freshener molecules are going to end up in the bottle, but most of them are going to end up in the room. The third one says water vapor at a pressure of 1 atm condenses to liquid water at the normal boiling point of water at 100 degrees Celsius. Okay, so what we have to think about is what's happening. So we have water vapor, which is a gas, that's going into the liquid state at a pressure of 1 atm, so that's STP, and that's happening at a temperature of 100 degrees Celsius, which is the boiling point of water. Okay, so what I would say is, okay, I have to think about what's happening at 100 degrees Celsius. Well, water is boiling from the liquid to the gaseous state, but we know, remember back to this chart, that when we have solid, this is heating up the temperature. This is where we had solids, solid to liquid equilibrium, liquids, liquid to gas equilibrium, and gas. So we know that in this area, at 100 degrees Celsius, that there's actually an equilibrium process occurring. Even though liquid is escaping into the gaseous state, gaseous molecules are being trapped back in the liquid state. So what this tells me is this is at equilibrium because of that chart, okay? So you can hopefully start to see that some of the stuff we've been talking about, which seemed so isolated before, is actually not isolated material. It was all foundational material to help us where we are now, which is understanding something as complex as thermodynamics. So what makes a process spontaneous? Well, it's going to depend on a lot of things, and we're going to talk about some of those things, okay? So explain why exothermic reactions are often spontaneous. Well, in order to understand that, remember these energy profile diagrams we talked about with enzymes and catalysts and activation energies? Well, we had two different types. We had the kind where the reactants were higher in energy than the products, and then we had the kind where the reactants were lower in energy than the products. And we said that this was the activation energy, EA, and this down here was the enthalpy that was released. And that's what made this an exothermic reaction. And over here, the activation energy was this hill right here, okay? And let's see, and then I should have used a different color, sorry guys. And so this was our endothermic reaction. Okay, so in this case, why is an exothermic reaction often spontaneous? Well, that's because the products are lower in energy than the reactants. There's a very low activation energy required to make that reaction occur, so very small EA value. Okay. So this says list some endothermic spontaneous reactions. So the one that I can think of that's the most common are those cold packs. They have the kind where you snap the packs and they heat up, like I think they're called hot hands. It's like an as seen on TV thing. We sold tons of them when I worked at Walgreens in college. And but they also make a cold pack where you snap the packs and they become cold. Oddly enough, when you mix baking soda and HCl, this is an endothermic reaction. There are others out there, but those are just the two that come to the top of my head when I'm asked that question. Okay, so they're spontaneous, but they're cold. When they're cold producing, that really means that they are heat absorbing, which is weird to think that those are related to each other. So while being exothermic usually means that you are a spontaneous reaction, it's not always guaranteed. Therefore, there has to be something else at play. So back up here, what makes a process spontaneous? It's not always whether or not it's endo or exothermic. There's a lot more involved, okay? That's just a part of it. So enthalpy is part of spontaneity, okay? But the other part that's going to be involved is called entropy, okay? And entropy is how I feel like our life is right now. Because entropy is a measure of how spread out or dispersed the energy of a system is among the different possible ways that a system can contain energy. But sometimes entropy is defined as the amount of disorder in the system. Now, the system, when it says it can exist in different ways, these are called microstates. So they're kind of like different scenarios, okay? Different scenarios. Now, Ludwig Boltzmann is the scientist. Kind of looks like a very grim individual, but he's the scientist that's attributed with our understanding of entropy and microstates. And so what it looks like is, say I have four particles, okay? And I have if I start thinking about all the different arrangements I could make of those particles, I could put them all in one box. I could put 3 in one box and 1 in a box by itself, or I can do 2 and 2. Okay, and so these are all the different possible arrangements. The more possible arrangements I have, the more disorder I have. So if I only had one particle, well, I really only have either the particle is here, these look like dice, or the particle is here. So this would be low disorder. It's only this or that, not a lot of options. So Ludwig, which I think it's Ludwig, but Ludwig is the last name of some of my cousins, and so I call them Ludwigs. Ludwig Boltzmann related the number of possible microstates to entropy through the following equation, which you don't need to memorize, okay? What I need you to know is that as the number of possibilities increase, the entropy increases, okay? And that's what S is. S is entropy. Another way to think about microstates is as if you were taking pictures of a situation. Each picture that's non-identical is another microstate. So when we talked about how molecules don't just stay still, they are moving, they can bend along their bonds, they can wag back and forth, they can rotate. And so taking individual pictures, you're going to get, it would be like taking a picture of my 5-year-old running around. There's a lot of disorder in that system because he's moving around and each picture would produce a different image. So explain how the following situations, thinking about what we just talked about, would affect the entropy of the situation. So if I increase the temperature, we're going to increase kinetic energy, which is increasing molecular motion. Because the molecules are moving more, this is going to cause an increase in entropy. So we're just building on all those things we've learned about. We've already learned the first 3. Okay. Dissolving solute into a solvent. Well, as I increase the solute, I am increasing the number of molecules, which if I think about my images up here, I'm going from 1 particle to 4. I'm going to increase, I'm going to write entropy for now until we get used to the capital S, okay? Entropy. Because we tend not to like entropy for the fact that it is an S as its variable, okay? So, as we dissolve more solute and solvent, we're increasing entropy. The other way I tell people is like this is increasing the number of people in your house, okay? You might be feeling this right now. If you have a ton of people in your house, it might feel a little more disordered if you're quarantining with 12 people in your house versus 3, okay? All right, size of the container. As we increase the container, we are allowing for more molecular movement, okay? So let's go back to up here. Let's say that instead of 2 boxes, I'm going to give these 4 molecules 3 boxes. So now I can do 4, or I can do 4, or I can do 4. So before, I just really had very limited options. But now I could put 3 in 1, or I could put 1, 1, and 2. So all of a sudden, having more boxes for my particles means there's more entropy. Now the phase of the compound is related back a little bit to kinetic molecular theory. So what we see is that gases tend to be more, oh my gosh, my stomach's growling. I hope y'all can't hear that. It happened to my other class's video last time. So gases tend to be more entropic than your solids, okay? And that's because solids don't typically move. So we're going to see that this is as molecular motion increases. Okay, actually I don't like the way that doesn't make sense to me. Okay, so entropy, I have this different on my handout and I decided to change it. Okay, so less entropy, more entropy. Less, more movement. Okay, I like that a lot better. All right, so because solids tend to not be, well, okay, remember we talked about their structures. Solids are rigid 3D structures. They do have a little bit of motion, but they're kind of like a bed spring. They're not going to move a lot. Whereas liquids are more fluid, for better or less terms. The molecules move around a lot more, and gases are the most. And so as molecular motion increases, entropy also increases. Okay? All right, so this is the end of lesson 26. So remember that the lessons are broken up a little bit differently based on the fact that I wanted to have more time at the end of the semester for some of these chapters, and so I adjusted the division of the material. And so we'll move into lesson 27 next. And so hopefully these videos are helpful, but please, if you have any questions or concerns while we are apart, you just need to email me, reach out to me in some way that you feel comfortable so that we can get your questions answered.